Well, welcome back. We are going to continue our journey and we're going to start discussing more about the shape of the atoms. We're going to be looking at electrons, and this kind of going is going to fall under the umbrella called quantum mechanics, which means we're going to be discussing a little bit of physics and some other interesting topics. This model is going to explain how the electrons have a very weird behavior. This model is going to explain pretty much how the electrons exist within an atom and how those electrons are going to determine the behavior of the atom itself, physical and chemical properties of the element itself. Now we know that metals are get oxidized, right? They like to give off electrons, and non-metals are going to wanna gain electrons. They like to be reduced. They want to gain electrons. And we also know the noble gases are inert. What that means is that they are satisfied with the number of electrons that they have. So with that in mind, it's this whole idea of quantum mechanics came from this gifted scientists such as Albert Einstein, Niels Bohr, Max Planck, and all of that. They started like realizing metals. Hey, metals like to give off electrons. Non-metals like to gain electrons. So with all of those observations, they start developing this and start pretty much explaining how those electrons make a huge difference in the atom itself. So let's go with the beginning of quantum mechanics. Um, what what this um, what's the word I'm looking for? I guess subject or umbrella of chemistry is gonna help us try to explain questions like why helium is an inert gas. Why is it that it's satisfied with the two electrons that it has? On the other hand, hydrogen is very reactive. But why is that? There's not much difference, even on the molar mass, there's not much difference between those two. And we have elements such as nitrogen, oxygen, chlorines that are considered diatomic elements. So all of those questions are going to try to, like, quantum mechanics is going to try to attempt to answer those questions. But before we go there, we need to realize something about the electrons. The electrons are among the smallest particles and they make up matter. Um, However, even though they're so small, they are going to determine the chemical and physical properties of matter. Because remember, since everything is it's going to be have electrons, they are going to determine how the matter is going to be. What I mean by that is, will it be a solid? Will it be a gas? Would it be a poisonous gas? So that behavior is determined by the electrons. Um, we are not going to directly observe the electron. It's impossible. They are very, very small. However, what we're going to see is the behavior that takes place. Even if we shine light of the electrons, we're going to see that something takes place. So we're going to be looking at the behavior that takes place when we do things to the electrons and we're trying to study the electrons. Now, I have put a few videos here to just kind of help explain this whole idea of quantum mechanic model. That was the idea that I was looking for. So just in case you want to have, just a better picture. But this theory, so this theory of quantum mechanics, in to formalize it, what it's going to do, to formalize our explanation, it's going to explain the manner which electrons exist and they behave. So by us trying to understand this, what's going to happen is that we're going to be able to do predictions on why electrons act a certain way. In addition, it's also going to explain some patterns on the periodic table. This model is going to explain why we have some elements that are very reactive and others are not. So it's just going to give us a overall bigger picture of what's going on, and you're going to explain why is it that some elements go together perfectly and some do not interact. But before we go into that, we are actually going to explore electrons and the behavior they have within an atom. But before doing that, so that's the goal, right? The goal is to explain electrons and how they behave. But before doing that, we are actually going to need to understand the properties of light. And we're going to see how light and electron have a lot in common. As quantum mechanics developed, interesting enough, they found that light had many of the characteristics as electrons, which made us study light first. So some properties of light are best described as thinking of light as a particle. And other properties of light is better described if you think that light is a wave. In the main definition, light is an electromagnetic radiation. It's a type of energy that is composed of oscillating electron and magnetic fields. And you're gonna see this when we move on to the next image. I'm gonna be able to explain that, but notice here, so here's it has the electromagnetic electric field and a magnetic field. The electron field is going to be a region where electrically charged particle experience a force. A magnetic field is going to be a region where magnetized particles experience a force. So that's basically what light is going to be composed of. All electromagnetic waves move through space at a constant speed, and that speed is going to be 3.00 times 10 to the 8 meters per second. So notice that unit, meters per second, and that is important because when we start talking about wavelengths, we're gonna change that, and we're gonna be looking at nanometers. So we're gonna have to be able to switch. And so this number is the speed of light. That is going to be the speed of light. So as promised, here's the image that I was telling you that kind of represents the electromagnetic radiation. This that you see here is going to be the oscillating mutually perpendicular electric and magnetic field. So they're propagating through space. The one in red, this in red is going to be a region where electrical particles experience a force. The one in blue is a field where magnetized particles experience a force. And then recall that there is that light has a speed, and light is faster than sound. If you remember, if you ever encounter thunderstorms, you see the why am I losing my mind? When you get electrocuted, what is it called? Anyways, you see that the light first, and then you hear the sound. So that's the idea, because light is going to be way faster than sound. I know all of this is gonna come back after I finish doing this. What is wrong with me? Anyways, so since we're gonna be looking at light as a wave, we need to characterize a wave. It has different characteristics. One of them is being its amplitude and its wavelength. So notice the amplitude. So the amplitude is going to determine the intensity of light. And basically it's gonna tell you how dim or how bright the light is. So the amplitude is gonna be this height of the wave. Now we also have wavelengths, and it's going to be represented by lambda, and is measured in meters or nanometers. The wavelength is measures the distance between the two adjacent crests. And like I said, it's going to be meters or nanometers. Those are going to be the units that we're going to be using. Let's see what else you need to know from this PowerPoint. Let's see. So the larger the amplitude, the more bright the light is going to be. Wavelengths, that's going to, every color is going to have a different wavelength. And we're gonna get to that in a minute. So just remember, every color, so because we're gonna be looking at different colors, is going to be represented by different wavelengths. The brightness of the color is gonna be determined by the amplitude of that wave. So here is informal definitions. The amplitude is the height of the wave, the distance between the node to the crest. The amplitude is gonna measure how intense the light is. The larger the amplitude, the brighter the light. The wavelength is going to measure the distance covered by the wave. You're gonna see how sometimes it's gonna that's going to change. And as it changes, we're going to be discussing every different colors. Now, there's other characteristics that we have to bring into play. We have frequency, which is represented by this letter. We're going to have frequency is the number of waves that pass through a point at a given period of time. The way that we're going to be measure that is going to be in hertz or seconds. So this means 1/2. So you want to keep this in mind because this is going to be beneficial for us. Frequency is going to be directly proportional to the speed at which the wavelength is traveling. So high frequency means high speed. Okay, high frequency, high speed. Longer, so now frequency and wavelength are inversely proportional. So the longer the wavelength, less frequency. Low wavelength, high frequency. And this is going to be related to the energy that that wavelength carries, because there's going to be energy involved. So remember, the frequency of the wave is directly proportional to the speed at which the wave is traveling. But frequency and wavelength are inversely proportional. And I'll give you some examples when it comes to that. So notice here it says the larger the amplitude, the more force it has. So that's the more frequently the waves strike, the more total force there is. So the more frequency it has more force, that means it's going to have more energy. So there is a relationship between there. For waves traveling at the same speed, the shorter the wavelength, the more frequency it has. What does this mean? This means that the wavelength and frequency of electromagnetic waves are inversely proportional. And I already told you that, right? It's going to be inversely proportional. So if wavelength goes up, frequency goes down. This is going to be the equation that we're going to relate speed of light equals the wavelength times the frequency. And remember, the speed of light is 3.8 times 10 to the 8th meters per second. And lambda is going to be your Lambda is going to be a wavelength, and then this is E. Now we can also manipulate this equation to solve for frequency, and it's important that you pay attention to your units. So C is gonna be your speed of light. This is the first of many equations you're gonna get, and that's a constant, right? That is a constant, so this is a given number. This is always going to be 3.8 times 10 to the 8th power. And then we have lambda, which needs to be in meters. But sometimes it'll be given to you in nanometers. So you need to know how to convert from meters to nanometers and vice versa. If we know well, we're gonna know the C because that's a constant, right? So if we know C, we can calculate, if we know C and we know wavelength, we can calculate frequency or the other way around. So because out of those three variables, if we know two, we can solve for the third one. So in general, here are going to be the characteristics of the wave, and you want to make sure that you are familiar with them. Okay, here's a calculation that you may want to try to practice. Calculate the wavelength of a red light. So remember, I told you that every light has a different wavelength with a frequency. So when you see frequency, you should be like, oh, what are they giving me? They're giving me V, right? And notice the units. Now, what they want is wavelength. So we're going to be looking for lambda. And usually when I ask for wavelength, always give it in nanometers. So remember, we know the equation that we're going to be using. Okay, so this is going to be, I don't know why it's not coming all of it. So it's going to be wavelength equals C over frequency, because this is the original equation. So all we did was manipulate it, right? Now, C, this is the speed of light, which is given to you, and this is the frequency, which is given to you, right? So when you do this math, your seconds are gonna cancel, and your answer is going to be in 6.49 times 10 to the negative 7 meters. But you need to go to nanometers. So how are we going to do that? I don't know why this is not showing. We're going to 1 nanometer equals 10 times 10 to the negative 9 meters. So when we do this calculation, you're going to end up with this wavelength, 6.49 times 10 to the second nanometers. It is extremely important that you know how to go from meters to nanometers. Okay? Pause it and try to answer this question by yourself. I'm gonna help you by giving you this. Try it on your own, and I will give you the answer in 1 second. Here's your answer. So if for some reason not everything is coming, but this is lambda equals so it's 2.98 meters. In this case, the answer was, since we're asking for wavelength. Now, if you can move forward and convert this to nanometers. Always when they're asking for wavelength, just give it to me in nanometers. The book decided to stop and give it to you in meters here, but it's good. It's a good habit to just give me your wavelengths in nanometers. Okay, we are going to move forward and we're going to start talking about color. Okay, moving on to color. Visible light. So moving on to color. Visible light is the light that we see with our human eye. And this is determined by which wavelength we actually are able to encounter. Because each wavelength is going to have a different color. And now each wavelength also has a frequency. These colors that we see are going to be red, orange, yellow, green, blue, violet, and they have different energy and they're going to have different wavelengths. White light that we actually comes from the sun, it's a mixture of its colors. What happens is that it's going to reflect on something, and that's when we actually see those beautiful colors that we're going to be looking. And then every wavelength, every object is absorbs different energy, and that's going to be the reflection that we see. Okay, moving on. Here is just a little bit of what we already went through. Notice that we have the different wavelengths and it has different colors. And the amplitude is going to have to be dealing with the brightness of the light. Wavelength and amplitude are independent properties. They're not related to each other. The wavelength determines the wavelength is going to determine the color, but the amplitude is going to determine the brightness. All of these colors can actually be observed in an electromagnetic spectrum, which you guys seen like the rainbow. Now, in these electromagnetic spectrums, you have to keep a couple of things in mind. Shorter wavelengths have high frequency, which that means that the light has a lot of energy. Radio waves have lower energy. What that means that they're not as dangerous. Gamma rays have high energy, so that means they're more dangerous. High energy electromagnetic radiation can potentially damage your biological molecules like your DNA, your proteins, and all of that. This image represents the electromagnetic spectrum. Visible light is only made up out of this tiny portion. So keep in mind that this is a magnification. Visible light is in between infrared radiation and ultraviolet radiation. That's it. That's that small portion. Short wavelengths have high frequency. And what that means is that it has greater energy. So notice here, the wavelengths here are short. I'm going to put different color. They're short and there's more frequency around this area. And this area has high energy. That's where we have your gamma ray and your X-ray. Notice here area, the wavelengths are longer and they're going to have less frequency and it has low energy. One of the questions that I can ask you is, what has more energy? Microwave, red color, or green color? So here's microwave, followed by red color, followed by green color. So the one that has more energy is green, because remember that visible, this is like the magnification. X-ray has longer wavelengths than gamma rays, because gamma rays has shorter wavelengths and it has more energy. So here's your dangerous area where you have high energy. So you want to make sure that you pay attention, study, and kind of know the trend. You want to know that the least dangerous are going to be radio waves because they have low energy and they have low frequency but low wavelength. Gamma rays have high energy, high frequency, and short wavelengths. Okay, so it's very important that you become familiar with this electromagnetic radiation spectrum. Now, a couple of other terms that we want to discuss, and that's going to be interference. So waves are going to interact with each other. This is gonna call interference. Now they can cancel each other or they can make themselves bigger depending on depending on the alignment that takes place when they interact. For example, I'm gonna go to this slide because it's gonna make it a bit better to explain. When you have two waves with equal amplitude and they are aligned, they're gonna overlap with each other and they are going to have a constructive interference. What that means is that they are gonna come together and they are going to create a wave that is twice the amplitude um, because of the way they interacted. On the other hand, let's say that you have waves that are coming what is called out of phase. They are not, the amplitude are not the same. What's gonna happen is, and they're not aligned, so you see they're not aligned. What's gonna happen is that they're going to cancel each other, and that's called disruptive interaction. So they're not going to overlap, okay? So here's your definitions on the slide before, and make sure you know, you go over them. Okay. We also have what's called diffractions. Waves are also going to diffract. What that means is that they're going to encounter a object. And what's gonna happen when they encounter an object or a slit, they are going to change their size, and it depending on how that takes place. So for example, notice here, the wave is going to encounter this obstacle with a slit. What's going to happen is that the wave is going to diffract, is going to bend in order to cross that slit. So that's what's called diffraction. The wave is going to bend. On the other hand, if we're talking about particles, the particles are not going to diffract. They're going to, once they encounter the barrier, they're not going to pass. So it's important to see that. Now, what happens when the wave encounters two different slits, two different obstacles? Now they can bend, and now you have these two new waves. Now these two new waves can interact with each other in phase or out of phase. So either constructive interference or disruptive interference. If they do constructive, they're just going to combine and create another wave with larger amplitude. If it's destructive, you're going to cancel the wave. And we're going to have, that's why we're gonna have this film where you're gonna have spots. It's not gonna be all one color because you're going to have different, some of them are gonna be in phase, some of them are gonna be out of phase, and that is responsible for this spaces that we have. So remember that waves are going to diffract. Particles do not diffract. They simply just pass through the opening or they don't pass through. And a wave can be diffracted by two obstacles, which can result in an interference, either constructive or disruptive, depending on on how they combine. Okay, so I think this is okay for now to just become familiar with light and characteristics. We're gonna move to a different topic, a little bit more complex. Okay, but this should be enough for now. Let's continue with this idea of what is called the photoelectric effect. And what this started by scientists observing that when light was being shined on a metal, metals were emitting electrons. So the light was being shined on the surface and electrons were being emitted. And the way they were able to kind of explain this observation was that the electrons the reason why the electrons were being emitted is because of the type of light that you were shining on them. Um, in other like in other words, what they were claiming is that there were two ways to explain it. So first, let me just explain that this is a little confusing. So let me try my best to try to narrow it down for you. So this was like prior to the 1900s, and pretty much we were just looking at light as a wave function. So what classical electromagnetic theory tried to explain for the reasoning of that these electrons were being ejected is that they said that the energy from the light was being transferred to the electrons in the metal, which resulted in those emissions. So if I have a light with energy, I'm giving the energy to the metal, and since the electrons are in the metal, those metals are going to eject. And they said, according to this explanation, they said that only amplitude had that effect. So basically, the intensity, the more intense the light was going to be, the more electrons were going to the more electrons that they were going to eject, right? So according to this theory, the rate which the electrons leave has to do with the photoelectric, is due to the photoelectric effect. So if you increase the intensity of the light, you're going to pretty much have more electrons shine. If you shine the electron with a dim light, you're not going to, you're going to have a lag time. You're not going to have electrons ejecting as fast. Now, there was a problem with this theory because what we're realizing is that electrons were being shined at different wavelengths, and some of them were being ejected, some of them were not. So what happened is that there was something that wasn't right. The results did not explain this. When this experiment was done, it did not support what classical theory said, because what the scientists, after this experiment, they found out that high frequency were ejecting electrons even though the light had low intensity without a lagging time. So basically they said, no, it doesn't depend on amplitude, it depends on frequency. Furthermore, that they realized that there was a what's called a threshold, that every wavelength, that wherever you were shining, it had to have a specific frequency. If you didn't have that frequency, you were not going to eject you were not going to eject any electrons, and that's what's called a threshold frequency. So it doesn't matter what you start, if you need to reach this this threshold in order for you to even start ejecting. So it's just became, this was an odd behavior, because what we realized that increasing the intensity does not change the threshold, because there's a specific threshold you're gonna have. So there's a minimum frequency that was needed for even the electrons to be emitted. Has nothing to do with amplitude. So now this started became confusing, and they're like, well, how are we going to explain that? You know, all of this craziness that's going on. Classical theories saw light as waves, but they realized that it had characteristics of particles too. So this is when it starts getting like, okay, you're looking at it as wave, but you're also looking at it as particles. So then we have a scientist that won a Nobel Prize, Einstein, was able to develop an equation that kind of says, hey, stop looking at it as a wave or as a particle. Look at it as both. So Einstein, this was like early 1900, like 1905, proposed an explanation to the photoelectric effect. And his explanation said that light energy comes in pockets. So you have pockets that like here's the light right here, here's the light. and there are pockets that are coming, and those pockets are going to be called photons. These pockets of light um, are going to depend on frequency according to the relationship that he's giving us here. So this is E stands for energy, where an age is going to be a Planck's constant. So those pockets of light are going to be quantum, like each pocket has a certain amount of energy. So unlike classical theory, in which light is viewed purely as a wave whose intensity was continuously variable, Einstein suggests that light was lumpy because those lumps, remember those pockets of energy, from his perspective of being light, not so basically what he was saying is those pockets are going to have a certain amount of energy, and you have to consider the frequency of that energy, of that energy that's, or I guess wave, and and if you know a constant, which is Planck's constant. Now the story where that number comes is a little bit more complex, so we're just gonna leave it alone. And we can calculate the energy. But let's say you don't know the frequency of that wavelength, but you know the wavelength. You can still figure out the energy of that photon, of that pocket of light, because you know the wavelength, you know what C is. C is going to be the speed of light, and H is going to be Planck's constant. So you can still figure it out how much energy is going to be put into the metal if you either know the frequency or you know the wavelength. Okay, so let's give you a practice problem here to see if you can do it. It's not, I don't know why it's not writing everything. So 3.7 times 10 to the second equals -9. Let me make sure the numbers, I don't know, for some reason they're not coming out. -7. Times 10 to the -34 times 10 to the 8 times 10 to the -7, -3 times 10 to the -3 times 10 to the -3. Okay, so notice in here, they're saying calculate the number of photons in a laser. But keep in mind that a laser is gonna have a whole bunch of photons. They wanna know how many numbers of photons are there with a wavelength. So you are giving wavelength and you are giving the total energy. They're telling you this whole thing has that much energy, but they just wanna know the number of photons. So you're going to use, you are giving the wavelength, and so that means you're going to be using this equation because you have two equations, right? The other equation is E equals HV, but you don't know the frequency. Since you don't know the frequency, you can't use that equation. So you're going to use the total. This is the total. No, they didn't give you the total energy. You're going to be able to, yeah, you are giving the total energy, right? No, you're gonna use this number later. So you're solving, first you have nanometers, you wanna convert it for meters. And the reason for that is because of Planck's constant. So notice that number, the Planck's constant, you wanna convert it to meters. Once you do that, you're gonna calculate the energy per photon. Once you figured out the energy per photon, you take that and divide it by the total energy, and that will give you the number of photons that you have in there. So take a minute to try to solve it by yourself. And then here's another question that I highly encourage you to pause it and try to answer. This is something that you need to memorize. This is another question that, and I kind of give you a hint to kind of help you. Oops. So try to solve it by yourself. And this is something that you are going to have on the test. Here's the answer. I don't know why it's not coming out. Tons. Make sure you double check the slides that I'm putting because for some reason in the video, it's not, it's, some of the signs are not showing. It's Planck's constant. This is the answer. Yeah. So try to do it by yourself. If not, we can always do it during discussion. Now let's give you some practice problems that do not involve math, involves knowing your spectrum. For example, order the following types of electromagnetic radiation: microwave, gamma rays, green light, red light, and ultraviolet, by wavelength. So you want to put short to long. So remember, short wavelength are going to have more energy. Long wavelengths are going to have less energy. You can also arrange it by frequency or by energy. So take time, look at that electromagnetic and see if you can answer this question. It will be best if you use your notes, but for right now, if you need to, go ahead and use them. Okay, so here's the answers. Okay, the next topic that we are going to keep talking about, it's going to be Einstein's idea of this quantized photoelectric effect. So Einstein idea was able to explain that photoelectric effect, right? That the emission of the electron from the metal depends whether or not a single photon has enough energy to remove the electron that is binding to the metal. So we call that binding energy. So think about it this way. Here's your metal, and we're gonna say that this metal is iron, okay? And you have electrons. You have little electrons here. Now, the electrons, there is an energy that is binding the electron to the metal. So let's say that energy is 200 kilojoules. I'm just making this up. Now, the light that you're shining, this metal has to have enough energy to overcome the binding energy. So if you hit it with 100 kilojoules, it's not going to be enough. It's not going to be enough. However, if you hit it with 300 kilojoules, you're going to bind, you're gonna eject the electrons, and on top of that, you're gonna have 100 kilojoules left of energy. That energy is gonna be converted to kinetic energy. And that this is where this is coming from. You can calculate how many kinetic energy you're going to have if you take the energy of the electron, of the photon, so in our case was 300 kilojoules, minus the binding energy, which is 200 kilojoules. So in this case, you will have 100 kilojoules of kinetic energy. And this is just an example. The binding energy will be given to you. Okay. Also, kinetic energy can be calculated using Planck's constant, the frequency minus the binding energy. So it's two ways of calculating kinetic energy, because that extra energy is going to be converted to kinetic energy. So here's another question. Think about this question and think about what the answer should be. So figure it out. You're striking it with yellow. what will happen if you struck it with ultraviolet? So think about it. Which one has more energy? Give you a minute to think about that answer. The answer is green. Okay, let's move on to a different topic, which is going to be spectra. So, as I mentioned, we were going to move to spectra. So, another observation about the atom was that atomic spectroscopy, which is a study on how electron radiation absorbs and gets emitted. So remember how I told you that when every object is going to be absorbing different amount of energy. So when atoms or molecules absorb energy, that energy it's released. That remember that kinetic energy is released in the form of light. So for example, when we light up fireworks, you see the light because what we're doing is it's releasing energy. When that emitted light, so when it releases, we call it emitted, passes through a prism, which is like this little triangle. It kind of breaks that light into a pattern of particular wavelengths. And we're gonna see unique patterns, and we're gonna see that it's going to be called a emission spectra, which you see here. You're gonna have different lights at different distances between each other, and that is gonna be unique for each material. And this is what we use. So we use emission spectrum enable for us to identify different elements. For example, if you had a gas and you were in a known gas, we can run some experiments and be able to see its unique emission spectrum. Every element is gonna have unique emission spectra. So it's gonna look different. It may be still red, green, and yellow, but the distances between those lines is going to be different. Here we have some gases. This one is mercury. This is mercury. This is helium, and this is hydrogen. Notice how they have specific colors, even though, you know, pink and reddish or violet are not that apart from each other, but the wavelength, the distance between those emission spectra is very different, and it allows to kind of identify that element, that gas. We can actually see this with fireworks. On the fireworks, you can actually, when you light it, you're going to see different colors. And the reason why it's different colors because you have different metals in there. So for example, lithium is this beautiful color. So that's what you'll be seeing. That's how you see these beautiful colors because of the emission spectra, the release of energy that you're having. Notice that the difference between white light, which is this white light versus helium or versus barium. White light is continuously, meaning there is no sudden interruption. So there is no object that wave is gonna cross. So there is no interruption in the intensity of light as a function of wavelength. The spectrum is going to consist of the spectrum is going to give you all the lights, but if there is no interruption, you're not going to have a breakage. But with other things like colors that we see, we actually see that it's not continuous. They consist of those bright lights, which are specific wavelengths with complete darkness. Now, classical physics could not explain this spectra. They were not, you know, they didn't understand why this happened. In fact, according to classical physics, the atoms are composed of electrons that are just orbiting the nucleus and should emit continuous white light. So they can't, when it comes down to it, they can't really explain it. What they're saying is the atoms should not be stable. This is classical. Obviously, this is like back in the days. I'm sure the way they see this is completely different. But don't quote me on that because physics is not my thing. So, but like, this is just to show you how unique it is. White light, it doesn't have any black line because it's not encountering any slits, any obstacles. So it's just continuously. Where we're talking about elements and all of that stuff, we actually see that this is completely darkness. Notice that here in both places for helium and barium, you have orange, but the wavelength, the distance between all of that, is completely different. Okay, now we are going to get to a Swedish mathematician that he analyzed the atomic spectra and he developed an equation to predict the wavelength. So we can predict the wavelength. So basically, he took this, he looked at this for hydrogen, which is not here, and he said, I want to predict the wavelength of each of those lines. He did it for hydrogen and he developed this equation. However, his equation gives a little insight um, because he basically only did this for hydrogen. And this equation works as long as N2 is bigger than N1. And I might explain what N is, but your N2 has to be your final destination. Your N1 is your initial destination. Notice that this is going to be the constant you're going to be using. And eventually you need to know how to solve for lambda. And it's the inverse, so you need to know how to take care of your inverse. So let me explain what N is. So as I mentioned, way back in the beginning, we have these electrons that are floating in these orbitals, in this, I told you like there were clouds. So another scientist, Niels Bohr, attempted to develop a model that explains the atomic spectra, like the one that you guys saw with the line. So he came out with this model where he says that the electrons travel around the nucleus. We already knew that. These orbitals have a fixed distance. So there is a fixed distance between this and this orbital. And they are going to be quantum size. What they mean is that each orbit has a certain amount of energy. Once you have filled that amount of energy, you have to move up. So the idea is that the electron is going to emit, when it comes down, it's going to emit energy in the form of light, because N5 is going to have more energy than N4. So basically, when you go down, you're emitting energy, you're releasing. When you go up, you absorbing energy, right? Because you're going from low energy to high energy. So when I mean that N1 to N2, all of that, that means that initial. So if I said the electron fell from N5 to N3, so my initial is going to be 5, my final is going to be 3, okay? But sometimes I can go upwards. I would say it went from N1 to N5. So N5 is my final and 1 is my initial. Now with this Bohr's model, there are some rules. The electrons are going to travel in orbitals. Those orbitals are fixed distances from the nucleus. We call that stationary states. Therefore, the energy of an electron is proportional to the distance the orbital from the orbit was from the nucleus. So the further you are, the more from the nucleus, that electron is going to have more energy. So if the electron is in N5, it has more energy than the electron being in N1. Electrons emit radiation when they jump. So if they're just sitting in the orbital, they're not emitting any energy. They're just sitting there. So if you're, think of it, if you're sitting, you're not emitting any energy. The minute you start running, jumping, walking, that's when you're emitting energy. The emit of energy is like when you emit energy, you're gonna emit it in the form of light. Think of the Bohr's model as the stairs. So just a ladder. So N6 has more energy than N1. An electron is never going to exist between orbitals. It has to be sitting in an orbital. An electron is only going to emit energy when it's in the process of moving. Also, notice that as we get higher up on the stairs, you are on this ladder, you're getting the distances are between your orbitals is smaller. So basically, that's what I just went. Electrons are held in orbitals around the nucleus that have defined energy levels. So each end has a certain amount of energy. Electrons do not normally emit energy when they're in the stationary state. A stationary state is when they're sitting in like the N1. When electrons move between levels, they absorb or emit energy. So if they are going from high to low, they are emitting energy, but when they're going from low to high, they absorbing energy. Electrons cannot exist between energy levels, and that's what I just mentioned. Okay, another way of looking at it is this way. So this is the electron is going from high to low. So this is your oh no, sorry, this is a different one. So this is from high to low. So that electron is relaxing. So because this is have more energy, this is more energy, there is going to be extra energy that is going to be released as a photon or in like light. This electron is absorbing energy because it's going from N1 to N3. So it needs energy. We have to excite it. That's what's called excitation. You're exciting the electron. Okay? All right, so I think this is a good stopping point before we get to the next level. We are going to continue with another equation. So in spite of the initial success of explaining the line spectrum of hydrogen using through the Bohr's model, there were some questions that were still unanswered. So Louis de Broglie replaced the Bohr's model with a wave-like nature electron equation, which is the one you see in this equation. He ran experiments which proved that electrons which thought to be as particles, also have a mass and have wave natures. So he predicted, de Broglie predicted that a wavelength of a particle is inversely proportional to its momentum. Because it is so small, the wave character of the electron is significant. Using this equation, we can calculate the wavelength if we know the mass, the velocity, and Planck's constant. Pay attention, the Planck's constant in this case has different units. So let's apply this equation. This equation will be given to you on your exam, so you don't have to memorize these equations. So a lot of equations in order to calculate wavelength, but you have to pay attention on what is given in order to determine which equation to properly use. Calculate the wavelength of an electron traveling, so they're giving you the momentum. Let me just put it so you guys can see. And so it's gonna be, this is equal for some reason. I don't know why this is not coming out like I wanted. Times 10 to the 6. Parentheses, from 10 to the negative 35th, and 10 to negative 34. Okay. Notice that in this case, they are giving you your velocity and you are giving, so the mass will be given. And the reason why it's not showing here, because according to this, you should already know the electron, the mass of the electron. And in this case, we want it in units of kilojoules. Why do we want it in kilojoules? Because of Planck's constant. So when you do this, you're going to realize that you have your Planck's constant, you have your mass and your velocity. So in this, you can actually calculate your wavelength. And it's in meters, which you can later convert to kilometers, to nanometers. So you have another question like this, which you can be giving on the exam. Pause it and try to solve it on your own. be careful because here they're telling you that the mass they're giving you in grams. So remember, because you're going to be using Planck's constant, you want to convert it to kilograms. And here's your answer. The first step will be to convert to kilograms. So your kilograms are going to be 1.675 times 10 to the negative 7. Once you have solved for that, you're going to apply it to this equation where you're going to be calculating the wavelength, of course. So times 10 to the negative 34, this is Planck's constant. This is the mass that was given, that you convert it to kilograms. And from here, this should be your answer. What we are going to go over next is this idea that an electron has complementary properties. What that means is that a single entity can behave as a wave and a particle. As we just saw in the Broglie's relationship, that relation that velocity and of the electron is related to its wave function. The position of the electron, however, is related to the nature particle. So we call this, so that the more we know about the position of the electron, the less we know about the speed of the electron. I hope that makes sense. So velocity of electron is related to the wave nature. The position of the electron has to do with the particle nature. We cannot simultaneously measure the position and the velocity of the electron. It's like a catch-22. The more you know one, the less you know the other. So that's what we say, that they have complementary properties, like catch-22. Because of that, Heisenberg, another scientist, kind of formalized this idea in an equation, this crazy equation. Don't worry, we're not gonna use it. It just helps explain. He stated that the products of the uncertainties in both position and speed of a particle is inversely proportional to its mass. Okay, which means we have to know the mass. This means that the more accurately you know about the position of these small particles, such as an electron, the less you know about the speed. So basically what I just told you in this ugly looking equation. So this equation pretty much is going to lead us to the probability. So it gives us a probability because we certainly cannot know it. So we're gonna get a probability of where you will find an electron in a certain amount of energy. When it has a certain amount of energy, where will you find the electron? And this is gonna be called orbitals. So based on that, we develop this equation where we pretty much are going to give you a probability. If an electron has this amount of energy, here's the probability of where you're going to find that electron. So what happens is calculations show that the size, the shape, the orientation in space of the orbital can be determined in 3 integers. And those 3 integers are going to be called quantum numbers. So basically, this probability is going to have 3 levels. So you're going to have a probability on the size of the orbital, which is going to be the principal quantum number n, the shape of the orbital, which is going to be the angular momentum quantum number, and the magnetic quantum number ML, which is going to be pretty much the orientation that is that orbital is going to have. So we're going to be focusing on 3 quantum numbers. Keep in mind that this is a probability of where can you find this electron it has a specific amount of energy. So think about it. If you have a uh, like someone with a lot of energy, you have a, you're I'm gonna be giving you a probability of what country that person is gonna be, what state, and what city. So think about it like that. We're going by levels. And all of this is a probability. So starting with the principal quantum number n. So that one is going to tell you the main energy, that size of the orbital. And this came from Bohr's model. That number n can be any integer from 1 through 7, well, greater than 1. So it can be 1, 2, 3, 4, 5, 6, and we can go up to 7. Why? Because we have 7 periods. The larger that value of n, the more energy the orbital has. What that means is that n equals 5 has more energy than n equals 1. Energies are defined as being negative. An electron will be E equals 0 when it just escaped from the atom. The larger value of n, the larger the orbital. As n gets larger, the amount of energy between the orbital is smaller, and we kind of already discussed that. Now, we can calculate the energy by using this equation, and that number that you see is Reber's constant. So this is for hydrogen. So we wanted to calculate the different amounts of energy. We can do it by using that equation. So for example, notice here, as you go higher, the energy increases. And remember, energy is going to be negative. So notice here, this is for hydrogen. This is just an example what was done for hydrogen. You're not gonna be calculating, so don't worry so much about that. Now, electrons are gonna transition from one orbital to the next one. So electron transition. In order to transition to a higher state, so let's say I'm in N3 and I'm trying to go to N5, the electron must gain that correct amount of energy corresponding to the difference between the final levels. So we need to make sure that if you're sitting here, you need to get enough energy to jump to that level. Electrons with higher energy are unstable. The more energy you have, you're gonna be unstable. And what's gonna happen is it's not gonna be happy here because I have more energy, I'm shaking, I'm dancing. I wanna fall to a lower orbital where I'm gonna have less energy. In the process of falling, I'm gonna release a photon, which is pretty much light. And that's what we call emission. Now, let's say from you are in this level, where's my color? We are in this level from N to N2. What is going to be my wavelength? Like at what wavelength I'm doing that? There is another equation to do that. And that is we're gonna be able to predict why is this equation like this? I don't know what's wrong with this. So we're going to be using this equation, which pretty much is the energy of the photon release minus that change of energy, negative, minus equals E final minus E initial. So we're going to be using this crazy looking equation, and don't worry, it's going to be better once I do some examples. So basically, we can calculate the wavelength that is the wavelength that is going to be that we're going to have when that happens. So for example, because remember that when it falls, it's going to remove energy. So if we go from N5 to N2 and we are at 434 wavelength, what that means is you're going to have that violet color and so on. So that's what we're gonna be determining. What is the wavelength if I fall from N5 to N3? And that's literally how your exam question will be mentioned. Like this, exactly like this. The only thing that I'm gonna change is the numbers. So if we ask this question and it's saying, calculate the wavelength. So the minute you see that, you should know that your answer should be in nanometers. Now be careful because this question is gonna look similar. That what is going to change is the word in red. I can ask you, calculate the wavelength. I can ask you, calculate the energy. I can ask you, calculate the frequency. Every equation that you're gonna use is gonna be different. So what you're going to do is, it says from N6 to N5. So this is your initial and your N5 is your final. Okay, so you're gonna use this equation and it's gonna be the energy. So we have the energy, it's gonna be equals negative 2.18 times 10 to the negative 18 times final minus initial. And that's gonna give me that much energy. But I don't want energy, I want wavelength. So you have to think, do you know another relationship, another equation that relates your energy with your wavelength? You do. It's going to be the wavelength equals Planck's constant, light, and E. Well, we just got E, right? This is our E. This is E. This is the speed of light, and this is a constant. So what happens? You are going to have, make sure you change it, right? Because this was, you have to make sure that the energy becomes positive. So notice that it's going to be times 10 to the negative 4. This is the speed of light times 10 to the 8th. And now you have your answer in meters, which you should convert to nanometers, right? Because it's best to convert it to nanometers. And you're gonna have a question just like this on the exam. Now, notice here, same question, but I changed it. And it says frequency. Frequency. So how will you do that? I'm asking you for frequency, but I'm also giving you that it's going from N2 to N5. So how will you do that? I want you to take a minute before we try to do it together. Well, we have a equation, right? So I have this equation. I have delta E equals negative 2.18 times 10 to the negative 18 joules times 1 in final minus 1 in initial, and their square. Okay, I also have another equation, delta E equals HV. And the equation we used from the last one was, we also have this one. So far, we also have this equation, lambda equals HCE. Okay, what am I looking for? Frequency. So I'm looking for frequency. So what does that mean? I'm looking for this. It's only in that equation, but I cannot jump directly into that equation because I don't have energy. So I'm gonna use this equation first. So it's going to be negative 2.18 times 10 to the negative 18. And sorry, this should be in should be N3 to N, from N2 to N3, sorry, N2 to N3. So that was correct. Okay, so I'll fix it on your slides. So the final is going to be 1, 3 square minus 1. Initial is going to be 2 square. And then when you do that for the math, let me put in the calculator. That should give you delta E equals 3.38 times 10 to the negative 19 joules. Now I have E. So now all I do is take this equation and manipulate it to where it's going to be V equals delta E divided by H. So it's going to be 3.02 times 10 to the negative 19 joules divided by 6.626 times 10 to the negative 34. And that should give me 4.57 times 10 to the 14s minus 1. And this makes sense because that is the unit of frequency. Take a minute, try to do it by yourself. Here's another question that I would like for you to try by yourself. And notice that in this case, I'm asking for the energy change. So basically, I'm just asking for delta E. Take a minute, try to do it by yourself. And the answer should be using this equation. Your final answer should be 4.58 times 10 to the negative 19. That's the equation from above. I didn't finish it, but you have it on the previous slide. Okay, so that was when becoming how to find energy wavelength. Oh, I didn't do a wavelength, but then you have some of the homework that you're going to be doing. Now we have to move on to the next quantum number, which is the angular momentum quantum number. Is an integer that's going to determine the shape of the orbital. The possible values are going to be 0, 1, 2, 3, and 4. However, for us not to become confused with n, we assign letters to this number. So it's important for you to remember that if I say L equals 0, I'm referring to S. That's the shape, and this is how S looks. If I'm referring to L equals 1, that means I'm talking about P. And P has 3 axes, 3P, 3X, and 3Y. PY. If I'm talking about D, I'm referring to, 3, I'm referring to D. If I'm referring to 4, I'm referring to S. And we're not going to get past that. So you want to make sure you memorize that, because that way we will avoid confusion. So now what is this S, this P, this D? Those are going to be the shape. So for example, S orbital is spherical. The P orbital is like you have 2 balloons tied to each other. Then you have the D orbital, and then you have the F orbitals. Don't worry, you won't have to draw them. However, you're going to have to understand it. You're going to be, each orbital is going to be described by the N integer, the L integer, and the M's of L integers. Okay, so the M's of L is the magnetic quantum number. It is the integer that specifies the orientation. So remember that N, it dispenses the size and how much energy. The L is going to be the shape, and the M's of L is going to say how it's aligned. That orbital is in a line. And it's going to vary from negative L to L. So for example, I just told you that if L is equals 2, the possibility of M's of L is going to be -2, -1, 0, 1, and 2. Okay, so let's say I tell you N, you have N equals 2, L equals 1, which means what? The ones that you have to remember is going to be, if you're talking about L equals 1, that means that it's going to be P. And P has 3 axes. So M's of L is going to be -1, 0 to 1. Okay? Each set is going to be represented by the N, the L, and the M's of L. Orbitals with the same values of N are in the same principal levels are also called principal shells. Okay, orbitals with the same values of N and L are said to be in the same sublevel. So it's just the terminology. So maybe this chart explains what I'm talking about. So in N1, you can only have LS. So because this is S, right? In N equals 2, you can have 2 sublevels, the S and the P, because this is S and this is P. In N equals 3, you can have 3 sublevels, the S, the P, and the D. And these are going to be your M's of L. And in each level, there's only a certain amount of electrons that you can put. And that's where the next chapter is going to come. So this is another table that it's going to be able to, so notice here, N equals 1. This is how many sublevels you can have, 1. N equals 2, you can have 2 sublevels. N equals 3, 3 sublevels. N equals 4, 4 sublevels. So for example, if I ask you, which of the subshells are N equals 3? Well, N equals 3 must have 3 sublevels. And you always gonna go in this order, S, P, D, and F. You're always must go in this order. So since our 3, you're gonna have the first 3. So the answer for this will be C, S, P, D. When you have L equals 0, we're talking about S. Notice that the difference between 1S and 2S is just going to be your size. It's going to be just the size. So this is how your S looks. Notice how your P looks, and your P is going to have three subshells. So -1, 0, and 1 because it has PX, PY, and PZ. It has three orientations. So notice here, so this will be PX, PY, and PZ. So this is your P orbitals. You don't need to know how to draw them. Then you have your L equals 2, which is your D, right? So then D is gonna have 5 orientations because it goes from negative M sub L, which is the orientation, is gonna go from -2 to 2. So -2, -1, 0, 1, and 2. And this is how it looks. Then we go with the more crazy one, which is the F orbital. We're not gonna touch it, but F orbital, what I do need you to know that it has 7 orientations, and because it goes from -3 to 3. And this is how it looks. You don't need to worry about how it looks. So this is an introduction to the next chapter. It's going to get a little bit more complicated, so make sure you watch this again and you understand it. But this completes the end of this chapter. We're gonna move on with the next quantum number. So far I gave you 3, N, L, and M sub L. I'm gonna give you the next one, which is M sub S in the next chapter. Stay tuned.